Hello, welcome. We are looking at evaluating limits analytically. There are several methods to evaluate limit analytically. The first method is by direct substitution. The second method is by simplification, where you simplify the expression before you apply the direct substitution. The third method is by factorization, where you factorize the expression before you apply the direct substitution. The fourth method is by rationalization, where you rationalize before you apply the method of substitution. The fifth method is trigonometric substitution. And the sixth method is by using L'Hopital's rule, which we'll look at it in depth when we look at derivatives. So these are the methods of solving limits analytically. So let's consider the following. Let B and C be real numbers, and let n be a positive integer. So B, C are real numbers, and n be a positive integer. Then, if you look at number 1, it says the limit of B as x approaches C is always equals to B. What does this mean? This means that the limit of a constant number as x approaches another constant number will be equal to the first constant number. And this can be explained on a graph. So this is the graph we have. We have the graph for the line y equals to 4, and we want to find the limit as x approaches 2. So as x approaches 2, we are going to be considering the left side of 2 and the right side of 2. So as we approach 2 from the right, the value we have on the y-axis is 4. And as we approach 2 from the left, the value again we have on the y-axis is also 4. So this tells us that the limit would definitely be 4. So if you have a constant, the limit of a constant as x approaches another constant is the same constant. Then number 2, we want to find the limit of x as x approaches C. So this is a typical example of direct substitution. So we want to find the limit of x as x approaches 2. In this case, all you have to do is direct substitution. You substitute 2 wherever you see x, and that gives you 2. Then for the third one, raised to the power n. So it's just going to be the same value substituted into the x raised to the power n, and that will give us our answer. So a typical example is the limit as x approaches 2, x raised to the power 3. So this becomes 2 raised to the power 3, which is 8. So these are the 3 basic limits you need to keep in mind whilst we look at the method of direct substitution. So here are examples. The limit of 3 as x approaches 2 is equals to 3. And the limit of x as x approaches negative 4 equals negative 4. Why? Because we only substitute the negative 4 directly into x, and that gives us negative 4. Then the limit of x squared as x approaches 2 equals to 4. Why? Because we are going to substitute these 2 into x, square that, and that gives us 4. So more examples to explain what we just said. So if I have the limit as x approaches 3 of x plus 2, this will be solved directly. How? I'm going to substitute 3 directly into x plus 2, which will give me 5. Example I. If I have the limit as x approaches negative 1 of x squared plus 3, how do I solve this? I'm just going to substitute negative 1 into x squared plus 3. And this gives us 1 plus 3, which equals to 4. So this is what we call the method of direct substitution. Let's proceed. Now, let's look at some properties of limits. Let B and c be real numbers, and let n be a positive integer, and let f and g be functions with the limits as follows. The limit of f of x as x approaches c equals to L, and the limit of g of x as x approaches c equals to k. So we can have scalar multiplication in limits. What does it mean? It means if I have a scalar quantity b multiplying the function f of x, I can take the b outside, find the limit of f of x, and multiply the answer of the limit with b. So first, I'll evaluate the limit before multiplying the limit by my constant b. Then number 2, the sum or difference property of a limit. If I have two functions, adding or subtracting, I'll first find the limit of the first function, find the limit of the second function, then add or subtract the result. A third, product. If I have two functions multiplying each other, I'll first find the limit of the first function, then find the limit of the second function, and then multiply the two results. The fourth property of a limit, if I have a rational function, I can find the limit of the numerator and find the limit of the denominator and divide the two answers. And that will give me the answer to the limit of the rational function, provided the denominator is not 0. The answer to the limit of the denominator is not 0. Power method. If I have a limit of a function that is raised to a power, I'm first going to find the limit of the function, then raise the answer of the limit to the same power. So these are basic properties of limits. Now let's look at an example using these properties of limits. So use the given information to evaluate the limit. The limit of f of x as x approaches c equals to 2, and the limit of g of x as x approaches c equals to 3. So we have question A. It says we should find the limit of 5 times g of x as x approaches c. So how do we solve this? Very simple. We already know the limit of g of x as x approaches c to be 3. So we are going to use first property of limit, which says that I take the 5 and multiply it to the limit as x approaches c of g of x. And this is going to give us 5 times 3, which is going to be 15. Then B, it says we should find the limit of f of x plus g of x as x approaches c. So here we are going to use the difference property to answer this. So we are going to have the limit as x approaches c of f of x plus the limit of g of x as x approaches c. And this will give us 2 plus 3, which is 5. So the answer is 5. And C, we have the limit of f of x times g of x as x approaches c. So how do we solve this? We said, first of all, find the limit of f of x as x approaches c and multiply it to the limit of g of x as x approaches c. We know that the answer to this is 2 times 3, which will give us 6. Question D. We're going to use this rule, which is the quotient property, to solve this. So we are going to have the limit of g of f of x as x approaches c divided by the limit of g of x as x approaches c. And this will give us 2 over 3. So this is how to use the properties of limits to evaluate the following questions. Now let's look more at the method of direct substitution. So I have a couple of examples here. Example A, it says we should find the limit of negative x squared plus 1 as x approaches 1. And to solve this, we are going to use direct substitution. So we substitute 1 wherever we see x. So this gives us negative 1 squared plus 1. And this will give us negative 1 plus 1, which will be equal to 0. So it means the limit of this is 0. Question B. We are first going to use the method of direct substitution. So we're going to substitute 3 wherever we see x. So this gives us square root of 3 plus 1 divided by 3 minus 4. And this gives us square root of 4 divided by 1, which gives us 2. Question C. Again, we are going to use the method of direct substitution. So we're going to substitute 0 wherever we see h. So this gives us 3, 0 squared plus 2 times 0. This gives us 0 plus 0, which is 0. Number D. So we're going to use direct substitution to solve this. Wherever we see h, we are going to substitute 0 in place of h. This will give us 3x squared minus 2x times 0 plus 5 times 0. And this gives us 3x squared minus 0 plus 0, which gives us 3x squared. So this is how to use the method of direct substitution to solve this kind of question. So the next method we are going to look at is the method of factorization. So we say when evaluating a limit, the technique you always want to try first is direct substitution. If a limit cannot be found using direct substitution, then you will use other techniques to try and evaluate the limit. Keep in mind that some functions do not have limits. So not all functions have limits, some do not have. If direct substitution yields 0 over 0, otherwise known as indeterminate form, then you cannot determine the limit in its current form. So it means you need to change it to a different form to be able to evaluate the limit. Encountering this form means you should try another technique. One way to deal with limits in this form is to use algebraic techniques like factoring, simplifying, rationalizing the denominator or the numerator. So let's look at factorization technique and how that applies to evaluating these kinds of limits. So the first question we have here is the limit of x squared plus x plus 2 all over x plus 1. And the first method we would like to try is direct substitution. So if we substitute 1 directly into this gives us 1 squared plus 1 plus 2 all over 1 plus 1, which gives us 4 over 2, which is 2. Question 2. So in this case, if we apply direct substitution, we get 2 times negative 1 squared minus negative 1 minus 3 divided by negative 1 plus 1. So this gives us 2 plus 1 minus 3 divided by 0. And this ends up giving us 0 over 0, which is indeterminate. So because this is the indeterminate form, we need to use a different method. So the method of substitution did not work. So which other method can we use? We said, first of all, you need to factorize. So factorize our numerator. And how do we do that? Very simple. This gives us 2x squared minus 3x plus 2x minus 3. So we have x outside, 2x minus 3, plus 1 outside, 2x minus 3. So this gives us 2x minus 3, x plus 1. So now that we have this as the factorization of our numerator, we'll rewrite our limit to be the limit as x approaches negative 1, 2x minus 3 times x plus 1 divided by x plus 1. This clearly cancels out, and now we can apply direct substitution to our limit 2x minus 3, which gives us negative 2 minus 3, which equals -5. So you need to know how to do your factorization beforehand. So let's move on to the next example. We want to find the limit of x cubed minus 1 all over x minus 1. And to solve this, very simple. So clearly, if you substitute 1, you end up with 1 minus 1 divided by 1 minus 1, which is 0 over 0. And this is indeterminate. So we said you need to factorize. So we apply the method of factorization to factorize our numerator before we apply direct substitution. So we apply the method of factorization to factorize this. And to do that, this gives us the limit as x approaches 1, x minus 1 times x squared plus x plus 1 divided by x minus 1. So clearly, we realize that x minus 1 will cancel x minus 1, leaving x squared plus 2 plus 1. Minus 1 squared minus 1 plus 1. And our final answer is equals to 1. In the next example, again, we have to apply the method of direct substitution first. So in this case, if you apply direct substitution, we end up with 9 minus 3 minus 6 divided by 3 plus minus 3 plus 3, which gives us 0 over 0. So clearly, we need a method of factorization. And clearly here, this gives us x plus 3, x minus 2, divided by x plus 3. So clearly, if we evaluate this, we end up with the limit as x approaches minus 3, x minus 2, which gives us minus 3 minus 2, which equals to minus 5. And that brings us to the end of the method of factorization. So as you can see, you first need to factorize your numerator in some cases before you can apply the direct substitution method. In this case, we also need to factorize the numerator. Then we apply the method of substitution on this part. And in this case, we also needed to factorize the numerator, which we did here, and apply the method of substitution to this part. But in this case, we applied direct substitution and it worked perfectly. So there was no need for factorization. So let's proceed. Now we want to look at the method of rationalization. So how do we apply the method of rationalization to rationalize the denominator? So here in this particular example, we have square root of x plus 1 minus 1 all over x. We want to find the limit as x approaches 0. So clearly, if we substitute 0, we are going to end up with 0 over 0. So that's not the way to go, so we need to apply a different method, which is rationalization. And to rationalize, we need to find the conjugate pair. So the conjugate pair of our numerator is going to be square root of x plus 1 plus 1. This is the conjugate pair. We are going to multiply both the numerator and denominator by this conjugate pair. So that gives us square root of x plus 1 plus 1 divided by square root of x plus 1 plus 1 times square root of x plus 1 minus 1 divided by x. And with the conjugate pair multiplication, very simple, all you have to do is take the one with the minus, square this and subtract. So if we do that, that gives us x plus 1 minus 1 all over x times square root of x plus 1 plus 1. So clearly, this gives us x divided by x times square root of x plus 1 plus 1. And now we can comfortably simplify this to the limit as x approaches 0 of 1 over square root of x plus 1 plus 1. And we substitute our 0 directly, we get square root of 0 plus 1 plus 1, which gives us 1 over 2. So that gives us the answer to this question. So all we did was to find a conjugate pair of the irrational function, which is just taking out this sign and changing it to the opposite sign. So we took out the minus, changed it to plus in this case. Then we multiply both the numerator and denominator by the conjugate pair. And we said to do this multiplication, all we need to do is to take the one with the negative, square this up, and square this part, and subtract. So if you square this, we get x plus 1. If you square 1, you get 1. And this times this gives us x times square root of x plus 1. X times square root of x plus 1. So now we have 1 minus 1, which is 0. You're left with only x. Then this part comes in. So clearly, x cancels x, and we are left with 1 divided by square root of x plus 1 plus 1. Now don't forget, this x here is multiplying everything here. So now, this is what we have. We do the direct substitution, and we have this, which gives us 1 over 2. So let's look at the next question. And again, we're going to apply the rationalization. So solution. So the conjugate pair to this part is going to be the opposite, which is square root of x plus 1 plus 2. So I'm going to multiply everything by that, x plus 1 plus 2 times square root of x plus 1 minus 2 divided by x minus 3. And again, this will give us x plus 1 minus 4 divided by x minus 3 into bracket square root of x plus 1 plus 2. So this gives us the limit as x approaches 3 of x minus 3 divided by x minus 3 times square root of x plus 1 plus 2. So x minus 3 and x minus 3 cancels out. We'll have the limit as x approaches 3 of 1 divided by square root of x plus 1 plus 2. And if we substitute x equals to 3, we have 1 over square root of 3 plus 1 plus 2. And this gives us 1 over 4. So that means the limit to this is 1 over 4. So what did we do? All we did was to find the conjugate pair to this, which is take this sign and change it to plus. That's what we have here. And we multiply the conjugate pair by the same fraction that we have. And we said to multiply these two, all we have to do, remember this is in a bracket. So to multiply these two, all we had to do was to look for the negative one, square this separately and square this and subtract. So if you square this, we get x plus 4. If you square 2, you get 4. Then we don't need to multiply this completely. We just need to attach them to each other as shown. Then we evaluate the numerator. We have x minus 3 And realize this can cancel that, so we'll have 1 over square root of x plus 1 plus 2. So now we can apply the direct substitution, giving us 1 over 4. So this is how to use the method of rationalization to solve limits. Now let's look at the method of simplification. So there are some limits that will require you to first simplify the expression before evaluating the limit. And a typical example is what we have here in this case. So if you substitute directly, you're going to end up with 0 over 0, because you get 1 over 4 minus 1 over 4, which is 0 over 0, divided by x, which is 0, so that gives us 0 over 0. So we need to apply the method of simplification first before we do direct substitution. And how do we apply the method of simplification? We simplify our numerator. A simple way to do this is to use the LCM by multiplying both sides by their denominator. So the first one, I will write this as 4 over 4 times 1 over x plus 4 to bracket minus 1 over 4 times x plus 4 divided by x plus 4, and all this divided by x. So this gives us 4 divided by 4 times x plus 4 minus x plus 4 divided by 4 times x plus 4 all over x. So now that we have the same denominator, we can easily simplify this expression. So this gives us 4 minus x plus 4. Remember, this is in brackets. So we'll end up with negative x divided by 4 into bracket x plus 4. So I'll write that division as 1 over x. So this will simplify to negative 1 over 4 times x plus 4. And now we can apply the direct substitution, which gives us negative 1 over 4 times 0 plus 4, which gives us negative 1 over 16. That becomes the answer to the limit. So first of all, what we did was we substituted directly. We had 0 over 0, which is indeterminate. Then we decided to simplify this expression. So to simplify, we found the LCM multiplied to both sides. That simplified to this form. Then we are able to simplify this form because they have the same denominators. All we need to do is to add or subtract the numerators. And we did that. 4 minus 4 is 0. We'll be left with minus x. So minus x divided by one of the denominators because they are the same. So we had 4 into bracket x plus 4. Then remember this divided by x, divided by x, divided by x. We had to reciprocate it, which is 1 over x. This x cancels out, and we have negative 1 over divided by 4 over x plus 4. Then we can apply our direct substitution, and that gives us negative 1 over 16. In the next example, we're going to apply the same thing. As you can see, they are similar. So in this case, it's going to be the same thing. We are going to first simplify before we apply the direct substitution. So this will give us 2 over 2 times 1 over 2 plus x minus 1 over 2 times 2 plus x divided by 2 plus x. So all divided by, so instead of writing all divided by, I'll just put here 1 over x. So this will simplify to 2 divided by 2 plus x times 2 minus 2 plus x divided by 2 times 2 plus x, all times 1 over x. So this will give us negative x divided by 2 times 2 plus x. All this into brackets times 1 over x, and x cancels out. So we now have the limit as x approaches 0 of negative 1 over 2 times 2 plus x. And this will give us negative 1 over 4. So this is how to use the method of simplification to solve limits. So the next topic we are looking at is the limits of trigonometric functions. And how do we solve limits using trigonometric functions? It's very simple. We substitute the constant into the variable x directly. So if I have the limit of sine x as x approaches c, this is going to just be sine of c. If I have the limit of cosine x as x approaches c, this is going to be substituting c wherever I see x, and that will be cosine c. Same applies to tan, same applies to cotan, the same applies to sec x, the same applies to cosecant x. So a typical example, if I have the limit of tan x as x approaches 0, wherever I see x, I replace it with 0, and that gives me tan 0, which is 0. And if I have the limit as x approaches pi of x cosine x, this I can separate into the limit as x the limit of x as x approaches pi, and the limit of cosine x as x approaches pi, which gives me pi cosine pi, which will end up giving us negative pi. The same applies here. I can find the limit and after that square the answer. So I take the square outside, substitute 0 in place of x, solve the limit and square the answer, which is still 0. However, there are special trigonometric limits that you need to know. And for now, we'll just deal with these two. So we have the limit of sine x over x as x approaches 0, always being equal to 1. So you need to memorize this. And also, we have the limit of 1 minus cosine x divided by x as x approaches 0 being equal to 0. There are proofs for these special trigonometric limits, but we are not looking at the proof for now. You don't need the proof. All you need is to know them, commit them to memory. So let's look at this example. You have to find the limit of tan x over x as x approaches 0. Now, clearly you can see that this limit looks nothing like none of the limits we are saying they are special. So what do? This is where we are going to apply our trigonometric substitutions. So here, I'm going to substitute in place of tan. We know that tan x is equals to sine x over cosine x. So this will become the limit as x approaches 0 of sine x over cosine x times 1 over x. And I can separate these guys as the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. And now it becomes simple to solve. I can easily solve this too using the limit that we have just considered. So clearly you can see that this can now be evaluated. This is a special limit which we have just discussed. So this gives us 1. Now we are going to evaluate this other limit, which is going to be the direct substitution 1 over cosine 0, which is going to give us 1 over 1. So therefore our answer is 1. So in this second example, it says we should find the limit of sine 4x over 4 as x approaches 0. So how do we solve this? To be able to solve this, we have to relate this to the special limit that we know. So we are going to rewrite this into this form so that we can use the special limit. So this can be written as 4 divided by 4 times sine 4x divided by x. And this gives us 4 sine 4x divided by 4x. So the limit as x approaches 0 of 4 sine 4x divided by 4x. Now we can take 4 outside and we'll have the limit as x approaches 0 sine 4x over 4x. Now you can treat this 4x as x, so clearly we know this will be 4 times 1, which is 4. And that is how to use this special limit to solve a question like this. So let's proceed by looking at more other examples on trigonometric limits which are very special. And again, we are going to use the fact that the limit as x approaches 0 of sine x over x equals to 1. So with the same idea, how do we transform this to that? So again, we are going to have 5 times 5 to sine 5x over 4x. And this will change to the limit as x approaches 0. We factor out the 4. So we'll have here 5 over 4 outside. This will give us sine 5x over 5x. So clearly we know this will be 5 over 4 times 1, which is 5 over 4. So this is how to use the special trigonometric identities to evaluate this kind. Now let's look at the last one. How do we evaluate this type? To evaluate this is very simple. We are going to have the limit as x approaches 0, sine x divided by, we factor out the x from the denominator, giving us 5x plus 1. So we can split this into two different limits, which will be sine x over x times the limit as x approaches 0, 1 over 5x plus 1. So this gives us 1. And this gives us 1 over 0 plus 1, which is 1. And our answer is 1. So clearly, this is how to use trigonometric identities to solve your limits. Now, we want to consider the squeeze theorem, or another word is called the sandwich theorem. And what this sandwich theorem talks about is pretty simple. You have the top bread and you have the bottom bread. So it says that if you are looking for the limit of the stuff in between these two breads, which is the egg, the bacon, all the yummy chicken and salad and all the cheese, if you are looking for the limit of a cheese or chicken function, it says that find a top bread function and a bottom bread function. If the limit of the top bread function is the same as the limit of the bottom bread function, then the function, your chicken and bacon and cheese function, will have the same limit as the limit of the top bread and the bottom bread. So in this case, if g of x is our bottom bread function, and h of x is our top bread function, and f of x is our cheese, bacon, and chicken function, then for all x which is not equal to c in some interval c, if we know the bottom bread function, which is g of x, and we know the top bread function, which is g of x, and the two are equal, which is L, then we can clearly say that our chicken, bacon, and cheese function, f, will have the same limit as L. So let's apply that. So in other words, if the sandwich function between two other functions, g of x and h of x, that both have the same limit as x approaches c, then f of x is forced to have the same limit as well. So let's analyze that. And to analyze that is very simple with an example. If 5 minus 3x minus x squared is less than g of x, less than or equal to g of x, and g of x is less than or equal to x plus 9, we want you to find the limit of g of x, which you don't know the function of g of x, but you know the top bread and the bottom bread function. So let's do that. We'll first find the limit as x approaches -2 of 5 minus 3x minus x squared. And this gives us direct substitution. 5 minus 3 times negative 2 minus negative 2 squared. And if you add everything up, this gives us negative 4. This gives us positive 6, which gives us 2, plus this, which gives us 7. Then let's find the limit of the top function, or the top bread, which is the limit as x approaches negative 2 of x plus 9, which also gives us 7. So therefore, that tells us that the limit as x approaches negative 2 of g of x would definitely be 7. And this is how to use the sandwich theorem. So the question then arises, how do I know the top bread and the bottom bread function? It's easy to compute that. And let's do that with example number B. So we know that this is a trigonometric function, and we know that cosine of any angle, cosine nx, is always between negative 1 and 1. So in other words, the minimum for cosine is negative 1, and the maximum for cosine is positive 1. And because we have x squared here, what we can do is to multiply this function by x squared. So in other words, I can decide to write this as negative 1 is less than cosine 1 over x, which is less than 1. And I'm being intentional. So because the question contains x squared, I'm going to intentionally multiply through by x squared. X squared cosine 1 over x is less than x squared. So clearly, I have my minimum and my maximum function, my bottom bread and top bread function. And now I can perform the limits. So I'll say the limit as x approaches 0 of negative x squared. And I also find the limit as x approaches 0 of x squared. And see the limit as x approaches 0 of x squared cosine 1 over x. So clearly, I know that the answer to this is 0. And the answer to this is 0. That tells me that the limit as x approaches 0 of x squared cosine 1 over x is definitely equal to 0, using the sandwich theorem or the squeeze theorem. So this is how to use your squeeze theorem to solve limits.